Hello everyone, today let's take a look at Quantipus number 94, which is a 4-part question that encapsulates everything that you'll ever need to know about Stirling numbers of the second kind. So let's look at part A first, asking us if we have 7 distinct letters, A, B, C, D, E, F, G, and we want to split them into 4 non-empty identical batches, and we're going to calculate it first using Stirling numbers of the second kind. This is exactly what we did in Quantipus number 58. So I have my 7 distinct letters here, and first I'm going to treat these groups as distinct, so I'm going to label them 1, 2, 3, and 4. So the first thing that we're going to do is we're going to take 7, raise it to the power of 4 here. So if these are distinct now, each letter has 4 possible choices for the group that it can go into, so we have 7 letters, so I'm going to take 4 and raise it to the power of 7. But I want non-empty, so I'm going to subtract off the cases where first 1 is empty. We're going to use inclusion-exclusion. So I have 4 ways to choose the empty set, and then when I do that, I'm going to have 3 places to put each of my letters, so 4 times 3 to the 7th. We know how to do this. Now I add back on the cases where I choose 2 to be empty. How many ways can I do that? Well, 4 choose 2 is equal to 6, so I add back on 6 times 2 to the 7th. And then finally, I subtract off my 3 empty cases, and there's only one way to put all 7 in one, obviously, and there's 4 choose 3 equals 4 ways to choose my 3 empty ones, so 4 times 1 here. This gives me 8,400. Now I need to remove the distinctness, so I can divide by 4 factorial because there's 4 factorial ways to permute these. I'm overcounting by a factor of 4 factorial in this number. So this is going to give me 350, and that's going to be my answer for part A. So now let's move on to part B, where it's asking me to solve the exact same problem, but now using integer partitions like we did in Quantipus number 81. And this is just to verify that we get the same answer that we do in part A. So what are my partitions of 7 into 4 groups such that none of them are empty? We know how to do this too from previous problems. I give 1 to each of my groups, then I've given out 4, so I have 3 left to hand out. So what are my partitions of 3 into 4 groups? Well, I'm going to have 3, 0, 0, 0, or I could do 2, 1, 0, 0, or I could do 1, 1, 0, 1, 1, 1, 0. So that's all I can do. These give me the final partitions of 4, 1, 1, 1, or I could have 3, 2, 1, 1, or I could have 2, 2, 2, 1. So these are all the possible partitions such that no group is empty of 7, but now we have to account for the distinctness of our objects. So given that our objects are distinct, how many times do we have to count this partition? 4, 1, 1, 1. Well, I have 7 objects, so I need to choose 4 of them to be in the group of 4. And once I do that, there's just going to be one way to put the remaining 3 objects into 3 groups. This gives me 35, so I have 35 ways to place my distinct objects into this partition. Now let's do it for this one. Okay, again, I have 7 objects. I choose 3 of them to be in my group of 3, and then when I do that, I have 4 objects remaining, and I'm going to choose 2 of them to be in my group of 2. So we just calculated it. It's going to be 35 times 6, which is going to give me 210. So now let's do it for this one finally. So I have 7 objects. I choose 2 of them for my first group of 2. Then I will have 5 objects. I choose 2 of them for my second group of 2. Then I have 3 objects, and I choose 2 of them for my third group of 2. And now since these are all equal in size, we can just permute them in 3 factorial ways, right? The 3 groups of 2, so we need to divide this by 3 factorial. Now this ends up giving me 105, and now we've calculated it for every single partition, so let's just add them up. And when you add these all up, you should also get 350. Alright, so now let's move on to the real interesting part, which is going to be part C and part D. So let me just remove this from the screen. Okay, so for part C, the only difference now is that the groups could be possibly empty, which makes it more complicated. So let's first do it using combinations of integer partitions. We already calculated the non-empty ones and summed them up, and we got 350. So now let's just add in the ones where some box is empty. So first let's do the partition where 3 boxes are empty. So there's only one way to do that, obviously, 7, 0, 0, 0. Now if we leave 2 boxes empty, well, I have 6, 1, 5, 2, and 4, 3, 0, 0. And then if I leave 1 box empty, well, then I'm going to have 5, 1, 1. I'm going to have 4, 2, 1, 0. I'm going to have 3, 3, 1, 0. And then I'm going to have 3, 2, 2, 0. And then if I leave no boxes empty, I obviously have these. So we just need to calculate all of these now. For 7, 0, 0, 0, it's just going to be 7, choose 7, right? There's only one way to put 7 distinct objects into one group. Now for 6, 1, 0, 0, we'll go through these pretty fast. This one's going to be 7, choose 6 equals 7. This one's going to be 7 choose 5 ways of choosing the 5 distinct elements for our group of 5, and that's going to give us 21. This one we choose 4 to be in our group of 4 and place the other 3 in the other group. It's going to give us 7 choose 4, which is 35. Again, here we choose 5 to be in our group of 5, 7 choose 5, which again is going to be 21. Now 4, 2, 1, 0, we have 7, we choose 4 to be in our group of 4, and then we choose 2 out of the remaining 3 to be in our group of 2. So this is 35 times 3, which is going to give us 105. For this one, we choose 3 to be in our first group of 3, and then we have to choose 3 more out of the remaining 4 to be in our second group of 3. And then we just need to divide by 2 factorial, which is 2, because the order of these groups does not matter. This is just when we have identical group size. So this one right here will give us 70, and now let's move on to our 3, 2, 2, 0. So I choose 3 to be in my group of 3, then I have 4 remaining. I choose 2 of them to be in my first group of 2, then I have 2 remaining. I choose 2 of them to be in my second group of 2, but these are repeats again, so the order of them doesn't matter, so I have to divide by 2 factorial. And this will give me 105 here. So now all that's left for me to do is just add all of these numbers up here. I already have 350, and I just add all these together, and when I do that, I get 715. Okay, so we did that. We've done that all before, right? So now the real interesting and new part is part D. So how do we get the same result using Stirling numbers? And remember, the Stirling philosophy is to 1, treat the groups as distinct, and then calculate the number of ways to place distinct items into distinct groups, and then 2, divide to remove the distinctness. So what wouldn't work is if you said, okay, I need to treat the groups as distinct. I have 4 different groups to place my 7 distinct items in, so I take 7 to the power of 4. Now I need to remove the distinctness, so I'm just going to divide by 4 factorial. And this doesn't work because not every single one of our partitions can be permuted 4 factorial times. It only works for the partitions where every subgroup is non-empty, like these up here. That's just because every single group has at least 1 element in it, so they're all guaranteed to be unique when permuted. It doesn't work for the partitions with multiple empty subsets like we see up here, right, where we have multiple zeros. The number of ways to permute these right here with 2 zeros would not be 4 factorial, it would be 4 factorial on 2 factorial, right, because we're doing the multinomial now. And for these with 3 zeros, it would not be 4 factorial, it would be 4 factorial on 3 factorial. So in our number 4 to the 7th, each one of these partitions would be counted not 24 times, but 12 times. So when we divide by 24, we are over dividing. We are dividing by too much for these right here. In fact, if we look at the Stirling number that we calculated in part A, which was this formula right here, and with this number, we were trying to calculate the number of distributions with all of their subsets having non-empty amounts of letters, right? So when we divided by 4 factorial to get rid of the distinctness that we were bringing in here, we got exactly this number up here, 350. This corresponds to these subsets over here. And if we look at this term, which was the number of ways to distribute the object such that at least one subset is empty, that's going to correspond to all of these, obviously. If you went and plug this into a calculator, this circled in red, you get 7,984. Over here, we are treating the groups as distinct, but over here, we are treating them as identical. And the cool thing is that when you add back on the distinctness to all of these terms and sum them up, you actually get this exact number. For instance, for this partition right here, if I was treating the groups as distinct, there would be 4 ways to permute this 7, right? So I take 1 and I'd multiply it by 4. And for these, when we had 2 empty subsets, there would be 12 ways of permuting them, right? It would be 4 factorial on 2 factorial. So if we multiplied all of these by 12 and then summed them up, and then if you looked at these and you saw that there are 4 factorial ways of permuting these because there's only one non-empty subset, then you multiply these by 24, right? All of these numbers by 24. And if you summed all of these up, you would get exactly this number back. Again, all of that was just to show when you're calculating possibly empty identical, you can't use the same strategy and take 4 to the 7th on 4 factorial. That's just because not every single partition has 4 factorial ways to permute it, right? These have 12 and this one has 4. But when you remove them from the equation by subtracting this term off, well then these all have 4 factorial ways of permuting them because there's no empty subsets. Okay, sorry about that tangent. Now let's actually go on and get back to solving part D using Stirling numbers only. And this is exactly why we've been grouping our integer partitions based on how many empty subsets they have. For instance, these have 1 empty subset, the ones up here have 2, and these have 0. It's because the number of empty subsets changes the factor that you have to divide by if you treat them first as distinct. So to solve part D, let's just go through case by case, right? When there's 1 0, when there's 0 zeros, like up here, when there's 2 zeros, and when there are 3 zeros. So when there were 0 zeros, right, when every subset was non-empty, we already calculated that in part A. It was S of 7, 4, and it gave us 350. Now let's calculate the number of ways when there's 1 0. And if you notice, if you look at this, right, we can just kind of ignore this 0 and kind of say that we're just partitioning 7 into 3 non-empty subgroups now, right? So I add on to this the Stirling number for 7, 3. Now for these ones up here with 2 zeros, let's just ignore the zeros and kind of say that we're partitioning 7 elements into 2 non-empty subgroups, right? So then again, you can see how I can add on S of 7, 2, and similarly I can add on S of 7, 1 for the case when 3 groups are empty. We know how to calculate the Stirling number for 7, 3. It's just going to be 3 to the 7th. Then we subtract off our cases where there are 1, 0. So we have 3 ways to choose those, and then 2 to the 7th ways to distribute the remainder. And then we add back on 3 times 1 to the 7th, and then we divide by 3 factorial. Now S of 7, 2 is going to be pretty easy as well. We know how to do it. We take 2 to the 7th minus 2 times 1 to the 7th, which is just 2, and then we divide by 2 factorial. For S of 7, 1, we have one group to distribute 7 items to. So we just take 1 to the 7th on 1 factorial, or just 1. We just say this is 1. So when I solve these out, I'm going to get 301 for this value. I'm going to get, well, this is 2 to the 7th minus 2 on 2, so it's 2 to the 6 minus 1. 2 to the 6 is 64, so this is 63, and then this is obviously 1. And then when I add all of these numbers up, 350 plus 301 plus 63 plus 1, I'm going to get exactly 715, which is exactly what we expect. So there it is. That is everything you'll ever need to know about Stirling numbers of the second kind. We worked through a lot of subcases, and I'm sorry if it got a little bit convoluted, but after you solve this problem, you should know Stirling numbers in and out.